You live in a galaxy. It's 100,000 light years across, contains somewhere around 200 billion stars. And you've never seen most of it because you're stuck on a rock about 2/3 of the way out from the center. So let's fix that. Sagittarius Idori. At the very center of the Milky Way, there's something massive, and for a long time, we couldn't actually see it. The galactic core is buried behind 26,000 light years of gas, dust, and stars. So how do you study something you can't look at? You watch everything around it. For over 30 years, astronomers tracked individual stars near the galactic center. One star in particular, called S2, became the key witness. S2 orbits the center of our galaxy every 16 years on an extremely elongated path, swinging within roughly 120 astronomical units of whatever it's orbiting at closest approach. That's closer than Pluto gets to our sun. But the thing S2 is orbiting is 4 million times the mass of the sun, and there's nothing visible there. That invisible drain at the center is Sagittarius A star, a supermassive black hole. 3 independent methods confirm this: long baseline stellar orbit tracking, infrared interferometry from the VLTI gravity instrument, and the Event Horizon Telescope's radio imaging. The EHT even captured a ring-like emission structure around it. To put the scale in perspective, resolving that image is like reading a newspaper on the moon from Earth. So we've got a 4 million solar mass black hole sitting at the center of everything. But what's surrounding it? The galactic bulge. So the center of the Milky Way has a bulge. You'd think it's just a big glowing ball of old stars sitting there like a cosmic doorknob. It's not. It's a bar. A rotating, elongated bar of stars stretched out with proportions of roughly 1 to 0.4 to 0.3, kind of like a cosmic baguette about 3.1 to 3.5 kiloparsecs long on each side, tilted about 27 degrees from our line of sight. It's not sitting still. It's spinning as a rigid structure inside the galaxy, like a ceiling fan embedded in a hurricane. The total mass packed into this bar and bulge region is about 18.5 to 18.8 billion times the mass of the sun. That's a lot of stuff crammed into the inner few kiloparsecs, but here's what's weird. About 17% of that mass, give or take 2%, is dark matter. Even here, in the densest stellar neighborhood of the entire galaxy, dark matter shows up uninvited. It's not just some shell around the outside. It penetrates the core. Remember that. It'll matter later. The bar rotates with a pattern speed of about 39 kilometers per second per kiloparsec. At a radius of about 6.1 kiloparsecs, stars orbit at exactly the same rate the bar spins. That's called the corrotation radius, and it's basically a gravitational conveyor belt funneling gas and stars inward toward the center, and the bulge's half-light radius, the zone containing half its brightness, extends out to about 2.75 kiloparsecs projected, so this central structure bleeds well into the inner disk. The boundary between core and disk isn't a line, it's a smear. Speaking of the disk, that's where most of the galaxy's visible action happens, and it comes in 2 very different layers. The thin and thick disks. So we've got this disk, you've seen the pictures, one flat plane of stars, nice and simple, except it's not one disk. It's 2, stacked on top of each other like cosmic pancakes with very different personalities. The thin disk is where most of the action happens. Young stars, active star formation, the sun, your whole life basically. It has an exponential scale height of roughly 280 parsecs, which means if you go about 280 parsecs above or below the midplane, the star density drops off sharply. It's flat. Impressively flat. And it stretches outward from the galactic center with a scale length of about 3.6 kiloparsecs, meaning that's roughly how far you go before the density halves as you move away from the center. Now the thick disk. Older stars, chemically enriched from billions of years of stellar recycling and way puffier. Its scale height is around 800 parsecs, nearly 3 times the thin disk. But it's more compact radially, hubby with a scale length of only about 2.1 to 2.7 kiloparsecs, depending on which stellar tracer you use. And here's the part that surprises people. The thick disk isn't some minor leftover. It contains roughly 10 to the power of 10 solar masses of stars. That's comparable to the thin disk. It's a structural equal. Where did it come from? Genuinely unresolved. One camp says it formed in place from a turbulent, chaotic early galaxy. The other says an ancient merger event puffed up a pre-existing thin disk. The answer changes how we reconstruct the entire early history of the Milky Way, and we don't have it yet. Quick honesty note, these exact numbers shift depending on whether you trace the disk using RR Lyrae stars, red giants, or kinematic selection. The qualitative picture, thin equals young and flat, thick equals old and puffy, is solid. The precise values are still method dependent, so we've got 2 disks, a bar-shaped bulge, and a supermassive black hole. But where do we fit into all of this? The Orion Arm. So where do we live in all of this? The Orion Arm, also called the local arm. This is our neighborhood, our street, our cosmic zip code. And for most of the 20th century, astronomers thought it was kind of embarrassing. Not a real spiral arm, just a minor spur, a little stub of stars wedged between the much grander Perseus and Sagittarius arms, like living in an alley between two avenues. But here's the problem, we're inside it. Trying to map the Orion arm from within the Orion arm is like trying to draw a floor plan of your house while locked in the bathroom. No windows, you can hear rooms, you know they're there. But good luck getting the proportions right. Then VLBI Moser parallax came along. These are insanely precise distance measurements using radio signals from star-forming regions, and they changed the picture completely. Turns out the Orion arm stretches at least 26,000 light-years long. That's around 8 kiloparsecs. That's not a spur. That's a legitimate major arm structure by any reasonable definition. The sun sits inside this arm at roughly 8 kiloparsecs from the galactic center. Not in the middle of the galaxy, not even close. We're embedded in one of its structural features, which is part of why mapping the whole thing is so frustratingly hard, and we're still not sure exactly what shape our arm has. Pitch angle measurements, basically how tightly the arm winds, range anywhere from about 10 degrees to 25 degrees depending on who's measuring and what sample they're using. That's a pretty wide spread. The debate over whether the Orion arm is a true major arm, a branch off Perseus, or something in between is genuinely still ongoing. Our classification is shifted multiple times as new data rolls in, the one arm we should know best, and we're still arguing about what it is. Science is fun like that. Speaking of arms, we can actually see from the outside. Let's talk about Perseus. The Perseus arm. So we've mapped our local neighborhood, time to look outward. The next major spiral arm beyond us is the Perseus arm, sitting about 9.08 kiloparsecs from the galactic center. And thanks to a technique called VLBI Moser parallax, we can map it with ridiculous precision. Here's how that works. Certain star-forming regions blast out microwave radiation from molecules called masers, kind of like natural lasers, but in the radio spectrum. By observing these masers from opposite sides of Earth's orbit, astronomers can triangulate their distances geometrically, no assumptions, no models, just straight up trigonometry, and when you plot all those maser sources for the Perseus arm, you get a surprisingly thin ribbon, only about 0.32 to 0.39 kiloparsecs wide. That's narrow. For a structure tens of thousands of light years long, it's basically a cosmic racing stripe. But here's where it gets interesting. The arm isn't a smooth curve. Models reveal a structural kink at a specific point in its sweep, where the pitch angle shifts from about 8.8 degrees to roughly degrees. The arm literally bends as it wraps around the galaxy, like someone bumped the table while drawing it. And the masers don't just give us positions, they give us velocity. Sources on the inner edge of the Perseus arm show a coherent inward motion of about 13.3 kilometers per second and a slight counter rotation of about 6 per second. These aren't random wobbles, they're streaming motion, gas and young stars being pulled in and through the arm by a spiral density wave. You're watching the arm's gravitational time. Now, the big question, is Perseus one of 4 distinct major arms, or does it branch from a shared 2-armed parent structure with the Sagittarius arm? It depends on which Madler dataset you trust, and honestly, jury's So what about the arm on the other side of the one hugging the bar itself? The Scutum Centaurus arm. So the Perseus arm is impressive, but it's kind of free-floating. It doesn't anchor to anything structural. The Scutum Centaurus arm is different. This one connects directly to the tip of the galactic bar. It's not just a spiral arm drifting through the disk, it's mechanically coupled to the bar itself, like a wrench bolted to a rotating engine. And that connection changes everything about what happens there. The arm stretches about 8 kiloparsecs in length and sweeps across roughly 100 degrees of galactic azimuth, making it one of the longest coherent spiral arm segments we've actually mapped. About 42 maser sources with precise VLBI parallax data now pinned down its geometry, and thousands of H2 regions cataloged by the WISE telescope fill in the broader picture. So this isn't guesswork. Modern-nated Scutum Centaurus is one of the best sampled arms in their galaxy. But the really wild part is what happens where the arm meets the bar. At that interface, masers show inward peculiar motions exceeding 20 kilometers per second toward the galactic center. That's not random turbulence, that's the bar's gravity actively funneling gas inward along the arm, like a conveyor belt feeding material toward the core. And all that gas piling up in one place does exactly what you'd expect. It forms stars, violently. Right at that bar arm junction sit RSGC1 and RSGC2, red supergiant clusters 1 and 2. These are some of the most massive young star clusters in the entire Milky Way, packed with red supergiants that trace recent extreme bursts of star formation. You've got galactic-scale machinery, the rotating bar, the spiraling arm, and right where they meet, stars are being forged in concentrated bursts like sparks flying off a grinding wheel, so we've mapped the arms. But what about everything above and below the disk? the galactic halo. So we've talked about the disk, the arms, the bar. All of that stuff rotates. It's organized, it follows rules. But surrounding all of it, like a ghost wrapped around a carousel, is something much older and much The stellar halo is a vast, diffuse envelope of ancient stars that surrounds the entire disk of the Milky Way. And these stars don't rotate neatly with everything else. They move on wild, highly eccentric orbits in basically every direction. Some plunge inward, some loop way out, some orbit nearly perpendicular to the disk. It's chaos. And that chaos is a fossil record. Most of these stars didn't form here. They're the shredded remains of smaller galaxies the Milky Way consumed billions of years ago. The halo is, in a very real sense, a graveyard, but it's a graveyard we can measure. Using RR Lyrae stars as distance tracers combined with Gaia spacecraft astrometry, astronomers have pinned down the inner halo's density profile as a power law with an exponent of negative 2.35 plus or minus 0.05. That means density drops off predictably as you move outward. But here's the interesting part. The flattening parameter is 0.57 plus or minus 0.02. That's called oblateness. It means the halo isn't a perfect sphere. It's squashed. Its vertical extent is only 57% of its horizontal extent, kind of like a basketball someone sat on. That shape tells us something about how the dark matter halo influenced its formation and how ancient mergers warped it over time. Now, the outer halo is a different story. Tracer stars get sparse out there. Substructure from old mergers like streams, shells, and overdensities messes up clean density fits, and different profile assumptions give you meaningfully different answers. So we're less certain about the edges. But here's what makes the halo really important. It's the transition zone. This is where the visible galaxy, all those stars and gas and dust, fades out, and the dark matter halo begins to dominate the mass budget. The stellar halo is basically the boundary layer between the Milky Way you can see and the invisible structure that actually holds them together. So what exactly is that invisible structure, and how much of it is there? Globular clusters. So scattered throughout the halo, riding those long looping orbits far above and below the disk, are some of the oldest things in the entire galaxy. Globular clusters. These are tight, gravitationally bound spheres of stars, hundreds of thousands of them, sometimes millions, all packed into a relatively tiny volume of space. And they're ancient. Most of them formed in the first few billion years of cosmic history. They were already old when the sun didn't exist yet. Think of them as fossils. Not fossils buried underground, but fossils in orbit. Each one is a snapshot of conditions from when the universe was still figuring itself out. The stars inside a given cluster tend to share similar ages and compositions because they formed together from the same cloud of gas in a burst of star formation that happened billions of years ago and then just stopped. Now here's the genuinely interesting question. Where did they come from? Some of them probably formed right here in the early Milky Way when our galaxy was young and gas-rich and chaotic. But others were likely stolen, captured from smaller dwarf galaxies that the Milky Way consumed over billions of years. The galaxy ate its neighbors and kept their jewelry. And we can actually try to figure out which is which because their orbits carry that hit. A cluster on a nice, well-behaved orbit might have formed in place. One on a weird, highly tilted eccentric path might be a souvenir from a galaxy that no longer exists. But here's the thing, they don't last forever. Over billions of years, the Milky Way's gravity slowly strips stars from these clusters, peeling them away through tidal force. The clusters dissolve gradually, feeding their stars into the halo itself. Some of the halo stars we talked about in the last section were probably born in globular clusters that no longer exist. Their distribution, spread across tens of kiloparsecs through the halo, also makes them incredibly useful. They're natural probes of how much mass the halo contains and how that mass is distributed, which raises a bigger question: what's actually out there holding all together? The Fermi bubbles. So we've talked about the disk, the arms, the bulge, the bar, the halo. You'd think that covers it. But in 2010, researchers analyzing data from the Fermi Gamma Ray Space Telescope found something nobody expected. Two enormous lobes of gamma ray and X-ray emission erupting above and below the galactic plane like a cosmic hourglass. They extend roughly 25,000 light-years in each direction from the galactic center. That means their combined height is comparable to the diameter of the entire galactic disk. Structures that large, that energetic, and that symmetrical do not show up by accident. You can't see them with your eyes. But in gamma rays, they dominate the sky. Two massive bubbles perfectly centered on Sagittarius A star and the galactic bulge ballooning out of the plane like something detonated at the core of our galaxy. And that's basically the question: what inflated them? There are two main ideas. The first is that Sagittarius A star, the supermassive black hole we talked about earlier, had a period of intense activity in the past. Not the quiet, barely eating black hole we see today, but something far more violent. blasting out jets of energy that carve these bubbles into the surrounding gas. The second idea is that a massive burst of star formation near the galactic center drove powerful winds outward, kind of like a galactic exhale, pushing hot gas thousands of light years above and below the disk. Both models make different predictions about what the edges of the bubbles should look like and what's going on inside them. And right now, we can't definitively tell which one is right. It might even be both, but here's what we do know. Whatever created the Fermi bubbles drew its energy from the same dense, chaotic central region we've been building to our video. The black hole, the bar arm interfaces where stars form like crazy, it all connects. Something enormous happened at the center of our galaxy. We just don't know exactly what. Yet, so if the Milky Way has all this structure, all this mass, all this visible stuff, what about the stuff we can't see? The dark matter halo. So here's where we are. We've mapped the black hole at the center to within a fraction of a percent. We've measured the bar, the bulge, the two disks, the spiral arms, the stellar halo, the clusters, the giant gamma-ray bubbles erupting from the core. We've tracked individual stars whipping around Sagittarius A star at thousands of kilometers per second. We've pinned down arm widths to a fraction of a kiloparsec. We have cataloged thousands of star-forming regions, traced streaming motions through spiral arms, and measured scale heights to the tens of parsecs. And all of it. What every single structure in this entire video is embedded inside something we cannot see. The dark matter halo isn't at the edge of the Milky Way. It is the Milky Way, at least in terms of mass and size. It's an invisible sphere of stuff we've never directly detected, extending tens to hundreds of kiloparsecs beyond the stellar disk, enveloping and outweighing everything visible by a huge factor. The stars, the gas, the dust, the spiral arms, all of it is basically decoration hanging from an invisible frame, and it doesn't just surround the galaxy. From the outside, it penetrates all the way to the core. Dynamical mass models of the inner galaxy, the bar and bulge region we covered earlier, show that even in there, dark matter accounts for about 17 plus or minus total mass. It's threaded through every structure we've talked about. Those same models also require an extra central mass component of roughly 0.2 times 10 to the 10 solar masses near the galactic center, possibly a nuclear disk or pseudo-bulge, which the dark matter alone can't explain. So even disentangling what's dark and what's normal matter in the innermost few kiloparsecs is genuinely complicated. But here's the part that should bother you. The total mass of the dark matter halo, the number that tells you how much the whole thing actually weighs, is not well pinned down. Constraining that number requires combining rotation curves, satellite galaxy dynamics, and tracers in the outer halo in ways that push way beyond what inner galaxy data alone can tell us. We don't have a clean single number, and that uncertainty isn't a failure of science. It's the honest frontier. We measured Sagittarius A star's mass to 10 significant figures. We mapped spiral arm pitch angles to fractions of a degree. And the structure that holds all of it together, the gravitational scaffold the entire Milky Way hangs from, is something we can't see, can't directly detect, and can't fully weigh. We don't know its exact density profile at large distances. We don't know what it's made of. We just know it's there. Because without it, none of this holds together. Every star, every gas cloud, every spiral arm in this video exists inside a structure we can only infer by watching how everything else moves. That's the Milky Way. Mostly invisible, mostly unknown, and absolute. If you enjoyed this video and want to see more, click the video on the screen now.